All right, molarity, acids, and bases. So, molarity is the number of moles of solute per 1 liter of solution. We use a capital M for molarity. Lowercase m is meters. Now, we also have a nice, beautiful molar here. When we're talking about molarity, we're not talking about your teeth. We're talking about the strength of solutions. That's down here. Molarity is the correct way to talk about how strong a solution is. Another way to talk about molarity is concentration. The higher the concentration, the stronger the solution, the higher the molarity. We'll come back to that because we have some words to talk about. Solute, if you remember from the last unit, is the amount of stuff that's dissolved in a solution. So the solution is the solute and the solvent. The solvent is what does the dissolving. The solute is what is dissolved. Molarity is how many moles of solute are in that solution. The more moles in that solution, the higher molarity. The stronger it is, the higher concentration. Just as a quick example, if we use Kool-Aid, water would be the solvent. The Kool-Aid and sugar would be the solvent. Kool-Aid powder, my bad. And the final drink is the solution. Check out the other videos on that. And then here we just have an example. 2 capital M solution is 2 moles of solute dissolved in 1 liter of solution. So that would be 2 moles of sugar dissolved in 1 liter of water. Or it could be 4 moles of solute dissolved in 2 liters of solution. There's a formula for that. We'll see it soon. And then the way to read it, 2 capital M, you read it as 2 molar. 0.5, whoops, that should be 0.5 M. 0.5 capital M is read as 0.5 molar, or 0.5 molar. Now, we're going to go back to here. Molarity is the correct way to talk about solutions. You don't say, it's strong. You talk about the molarity of it. And higher molarity is a stronger solution. Higher molarity is more concentrated, so higher concentration is higher strength. Nice little logic sequence for you. And then, to put that in perspective, here's a nice little depiction. This is me. Dang, look at those gains. My molarity is greater than Piston Cup Productions' molarity, which is why I am full of gains, and Piston Cup Productions is a teeny little pipsqueak. His gains are weak because his molarity is lower, which means he is lower strength, he is less concentrated. So, Piston Cup Productions, weak sauce. Me, great sauce. Yay. Now your formula for molarity. It's moles of solute divided by liters of solution. And then here we have the example. We have 10 moles of sugar and 4 liters of Kool-Aid drink. That means that Kool-Aid has a molarity of 2.5. 2.5 molarity. There's also this concept of dilution. It's where you decrease concentrations, you decrease molarity by adding more solvent. So if we took this Kool-Aid solution of 2.5 molar, and let's say we double the amount of water. If it was 4, now it's 8. So the new molarity is 1.25 molar. We have diluted it. We've reduced the concentration. We've added more solvent. Next, we have acids and bases. We've talked about these a little bit when we talked about neutralization reactions. Here are some pro tips that you need to know. Acids all start with H, hydrogen. So any acid that you see, H2SO4, sulfuric acid, hydrochloric acid, HCl, hydrobromic acid, HBr, nitric acid, HNO3. They all start with hydrogen. They all start with H. Now, chemically, what makes something an acid isn't just that it starts with H. For instance, water, H2O, starts with H, but it is not an acid. What makes something an acid is that it forms hydrogen ions when you mix it with water. So you take an acid, you pour it in water, and it dissociates into hydrogen ions. And then a neat little fact that I like to ask as multiple choice questions. Acids taste sour. So some common acids you've heard of. Citric acid, it's what's in orange juice. That citric acid is what makes it taste sour. Vinegar is acetic acid mixed with water. Acetic acid, that's why it tastes sour. Bases all end with OH. And if you remember, OH is a polyatomic ion, it is hydroxide. Now again, OH in organic chemistry is also alcohols, but what makes a base is that it forms hydroxide ions when you mix it with water. But that's for smart people. For us, we're just going to be concerned with if it ends with OH, it is a base. The most common base you'll see is sodium hydroxide, NaOH. That's the one I'll usually use as an example. And then, just like acids tasting sour is a little fun fact, bases feel slippery. Yeah. Now, acids and bases are both good electrolytes. Electrolytes mean that it can conduct electricity. If we look at this little graph, we have a light bulb connected to a wire, connected to another wire, connected to another wire. At no point are these two wires connected, but right there you can see that they're not touching. If this solution, this liquid that they're in, is electrolytic, if it is a good electrolyte, this light will still glow. The stronger the electrolyte, the better the light will glow. Here we have only a few ions. This is a not very good electrolyte. This is a weak electrolyte. The light is on, but only a little bit. It's pretty weak. Here you have many ions, you have a lot of them. This is a strong electrolyte. And if you look, the bulb is much brighter. Look at that. So much bigger and stronger. So electrolytes conduct electricity. Acids and bases are good electrolytes. They are good electrolytes because of these hydroxide ions and hydrogen ions that they form. Okay. Now, when you mix an acid and a base, neutralization happens. We talked about this already. This is just review. Neutralization means they cancel each other out. Those hydrogen ions and hydroxide ions, when you mix an acid and a base, it forms those ions. When you combine hydrogen and hydroxide, you get water. In a neutralization reaction, you will always end up with a salt and a base. And salts are just ionic compounds that are a combination of a metal and a nonmetal. For instance, NaCl. That's table salt. MgBr2, magnesium bromide. That's also a salt. Anytime a neutralization reaction happens, you will always get a salt and water. Great. Now, another way to measure the strength of acids and bases is with the pH scale. It still relies on molarity, but we're just going to call it the pH scale and not worry about the math part. The pH scale goes from 0 to 14. You've probably remembered this at least a little bit from middle school. pH is less than 7, that's a less than symbol, are acids. If the pH is greater than 7, that's a greater than sign, it is a base. And the further away from 7 you are, the stronger it is. So 0 is farthest away from 7, so 0 are the strongest acids, and then all the way up to 6.9, which is close to 7, those are the weakest acids. And then bases are the exact opposite. The further away from 7, for bases, 14 is the furthest away you can get. That's the strongest base. 7.1 is your weakest base because it's closest to 7. And then the final thing you need to know is that the pH scale is logarithmic. Logarithmic is probably a new word that you haven't heard of before, but logarithmic means that each step means there's an increase of 10 times. So then we have our examples. If you have a pH of 3, you are 100% stronger than a pH of 5. So if we have an acid that is a 3, it is 100 times more acidic than something with a pH of 5. Your pH of 3 would be 10 times weaker than something with a pH of 2. You just count the number of steps, and then it's 10 times that number of steps. Well, 10 to that power. So 10 to the x, where x equals number of steps. Then the second example is a base. You have a base with a pH of 12. It's 1,000 times more alkaline, basic, than something with a pH of 9. And it's 10 times weaker than a base with a pH of 14. Okay, actually that's another word to write down. Acids are acidic. Bases are alkaline. There we go. Fun little vocabulary words for us. Okay. You're going to use this video. Go to Google Classroom. Answer the questions that you have.